Just finishing setting up things now. But yeah, so this week we have kind of like the usual arrangement of things in our program. And we will be going to the quantum experience for the latter half of the lab. We're just but we will have like a longer kind of intro, just because of we are going to be doing a lot more Python coding this week, and we're going to be using like we're going to be functionalizing our code, which we kind of started doing last week, where we created functions to like encode our message or like our bit that we were trying to send to Bob from Alice and then decode that by Bob. So we'll be doing something similar this week, but for a little bit more complicated of a protocol. So as usual, we do have our Canvas attendance quiz, and I will start the Zoom poll to get a feel for where you guys are at as far as material this week in lab. So this week's question for the Canvas attendance quiz is on a scale of 1 to 5, how comfortable are you with creating and executing circuits in Qiskit? And then for the Zoom feedback, it's the same as usual. And this week we discussed quantum key distribution. Specifically, we will be doing a version of BB84, which is kind of like the most standard, or not most standard, it's kind of the most standard quantum key distribution or QKD protocol that everyone kind of learns about first. Cool. So I'm getting a lot more uncertainty this week from the attendance or from the like pre-lab Zoom feedback. I'm like we're about half on a 3 and then the remainder on 4s and 5s. Funnily enough, there are 0 people that have put 1 or 2. So you guys are very, very confident in being not confident, but not like completely confused. So that's kind of good. Like that's kind of ideal actually. If everyone was on a 3 every week at the point of going to lab, that's probably a pretty optimal place to be, just because then you're getting something substantial out of the lab section where we kind of go through material more in depth and implement some of the stuff. But you understood like enough of the material and from lecture that you're not like overwhelmed. So very interesting this week. Okay. So the questions that we've gotten the most the past few weeks have been primarily on entangled states, which makes sense because entanglement is really, really interesting and entangled states are a little bit confusing. I think the most, I guess, so the way that you're typically taught about entanglement is, oop, there it is, it's entangled now. And the way you look to see if it's entangled is if you have, oh, this is in red, let me change that. If you have 2 states, like our 0, 0 plus 1 Bell state, you can see if you know, like let's say this is A or Alice, and this is B or Bob. You can see if you know Alice's state, you automatically know Bob's state. If you instead had a state like 0, 1 plus 0, 0, if you know Alice's state is 0, then Bob's state could be 0 or 1. So this is entangled, and this is not entangled. And that's kind of the most intuitive way to think about entanglement for the general case. Any case where you can create a state where like where the state of one qubit informs the state of the other qubits means that those states are entangled. Or it's not, I guess it's not like you don't change the other qubit state by virtue of one qubit state. And if you do try to measure like qubit A's state, you do collapse the entanglement. That doesn't mean that you don't like know, well, it's a bit like, I don't want to get too much into the weeds because it is like a pretty complex topic. But doing something to qubit A does not affect qubit B. the way to think about entanglement is just that um, the state that qubit A is in will also give you information about the state that qubit B is in, simply because mathematically it is impossible for you to know, it is mathematically impossible to be in a state where you do not know the state of qubit B given the state of qubit A. So the same thing goes for like our other Bell states, where we have something like this. Um, in both cases, like if Alice's qubit is 0 or if Alice's qubit is 1, you know the state of Bob's qubit regardless. Um, so this concept is very closely related to superposition. Um, so you can say that all entangled states are superposition states. It's not meaningful, like you have to be in some kind of superposition to have a kind of added state where you have some chance of being in one like energy basis state or another energy basis state. um, you have to be in a superposition state to get this kind of math, where there is some chance of both. If your qubits are just in like 0, 0 with like 100% probability, that's not an entangled state. That's just that they are both in their ground state. So all entanglement or all entangled states are superposition states. However, entanglement is an extra requirement on top of it, where this state is also still in a superposition, as is this guy. This guy is also in a superposition, but um, this state is not entangled because the state, or like Alice's qubit can be in, or if Alice's qubit is in the 0 state, which it must be to be in this state, Bob's qubit can be in either the 0 or the 1 state, which is not, so Alice's qubit does not give you any information about Bob's qubit. Yeah, and Elena's put a very good point. Just one qubit can be in a superposition, but you can't have one qubit in entanglement, because entanglement is inherently a multi-qubit state. You need to have at least 2 qubits, but you can have more than 2 qubits. So a very common like 3 or more qubit state is the GHZ state. Like the prototypical one is a 3 qubit state, but I believe people sometimes call more qubit states like kind of like GHZ adjacent. There are also noon states, which are like 4 or more typically. And these are all types of states. There's also W states. And these are all kind of named after the shape that their like entangled state looks like. Like with a W, you could see like you have like a 1, 0, 1, look kind of like a W. I'm not going to go into too much depth into these states because I don't like have all them like in detail off the top of my head, like for variations, because there are a lot of variations in these states. But there are a lot of like like a multipartite, I guess, entangled states where you have more than 2 qubits involved. But when you get to more qubits being involved, a lot of times you have to start distinguishing between like maximally entangled states and entangled states that are not maximally entangled. So when you have like 0, 0, and 1, 1, this is also maximally entangled, which just means you are as entangled as you can possibly be. You can still be in an entangled state that is not maximally entangled because you maybe have like many parties involved, and you don't have like absolute knowledge over all the rest of the parties by just like knowing the state of one. So that is a like something to account for, that you can be in entangled states that are not like what you're familiar with. That's also kind of in the weeds a bit. But a lot of times people will talk about, when we were talking about quantum measurement, it is common to talk about measurement as you entangling your qubit with your measurement device. So your measurement device starts to impact the state of your qubit. And so like that's how you would end up with when you measure or when you like perform a measurement on your measurement device, um, you are ending up with either a 0 or a 1 state. That's like the basis that you're measuring in. Um, and so it makes sense that your qubit would then also end up in a 0 or a 1 state. However, with these processes, these are not like necessarily maximally entangled, and they are impacted by like dissipative properties from like coupling to your environment or other things like that. So that's these first two bullet points. We've made it through. The third one, can we use entangled states to send information faster than the speed of light? No. No, we cannot. Not as far as we know or we have any theories to back up. As far as we know, all information propagation is limited to the speed of light. Maybe in a century we'll think we were such fools thinking that that was truly a limit. But for now, to the best of our knowledge, there is no way to send information faster than the speed of light ever. And that's why like these entangled states, like if when we create an entangled state, we typically do it by bringing the qubits like together, or we'll shoot like, or if we want to kind of distribute entanglement, there's some research going on. Specifically, one of my lab mates did some experiments on creating noon states and distributing entanglement using photons. So you could entangle like a qubit with a photon, send that photon down, and then entangle that photon with like another qubit that's nearby there and distribute entanglement that way. But that photon is still going at the speed of light, and so you are still like spreading information at the speed of light. Alternatively, you could like create an entangled pair of photons and then shoot them away from each other. And I guess maybe you could do twice the speed of light with that. But that's like, I don't know, that's a bit weird. It's a bit of a weird thought. I just had the thought and I don't like it because it makes me kind of uncomfortable. But yes, and you are pretty much limited to the speed of light. Your information is never actually propagating faster than that. But it does depend on the frame that you're operating in. So are there any further questions that are more conceptual on entanglement or otherwise? I know that was like a lot of information pretty quickly. These are very important concepts, but they're also fairly confusing concepts. And I didn't really feel like confident in like I guess entanglement until I kind of did it more mathematically with like tensors, which we have done a bit, but we haven't done it explicitly in lab. I believe you had some homework problems on it though. Angela has asked, how does the last question relate to the EPR paradox? So the EPR paradox is like it's the Einstein, I forget what P is, Rosen paradox, which has to do with there's like some things with like Bell state measurement that it's a bit complicated, so I don't want to go into detail on like how the EPR paradox works. I feel like it would be a good thing to touch on in lab. I'll make a note of that, or in lecture or lab. But it does not like you still cannot send information faster than the speed of light with like it doesn't like we have not found any like conclusive evidence. So yeah, it is a paradox. It's a bit like it's all a very complicated topic. So I don't want to go into too much detail on it because we do have quite a bit of material to go through. I also like haven't gone through these proofs in like a couple of years, so I don't want to do them wrong. Okay. Okay, with that, I'll get on to the material for this week. So this week, the lecture portion, I guess, is primarily going to be for coding. Oh, and also if you want to know more about like the EPR paradox, other things, definitely post it on Piazza, and I can give you a more detailed response there, or like another TA can. It's a bit, it's quite technical, I guess, to go through in lab. Okay, so this first section of the lab will be on reviewing important coding concepts like generating random bits, which we'll be using, like we are going to be creating like a random key and distributing it between Alice and Bob. And we will be doing this bit generation and appending each additional bit to our full, like, I guess, key length. And then we'll have to append some of these lists together for some purposes. And then we'll go over creating quantum circuits using, like, by functionalizing our code, so we can create a quantum circuit for any given key without having to type any new code. And then we'll go into the implementation in the IBM quantum experience. And then, because this is a recorded section, we will go into the optional content where we decode and I guess do like, we're creating, like, this protocol creates a symmetric key if you're familiar with encryption. And so we will actually be creating our symmetric key at this final step. But we might go over time to get to that. Okay, so the first step is to generate random bits. So we do need both Alice and Bob to be able to generate these random bits to perform our quantum key distribution protocol. We don't want to just create the same key every time, so we need to have some random bits created. The first step will be Alice creates random bits to choose the states she wants to encode, and then additionally, she needs to choose the bases she wants to encode the states in. So we're going to be using the standard bases that we've used in the course, and also the standard bases for this protocol, which are just the Z basis or the energy basis, and then the plus minus basis. I guess we'll put that in parentheses, I don't know. Bob will then generate random bits to choose which bases he's going to measure the qubits in. So Bob does not actually know the bases that Alice chose. That doesn't matter. What they're going to do, they're both going to just do whatever they please, pretty much. Alice is going to send her bits to Bob, which I guess is, oh, we don't have the rest of it on this. Yeah. Me unzoom. Okay. Alice is going to send her bits to Bob. Bob is going to measure them in his basis. And this is all, like, this was all covered in lecture, I guess. And then Bob, like, Alice is going to tell Bob what basis she used, and then he's going to compare what bits he had, and then he's going to send, Bob is going to compare what bits he ended up with based on measuring in his basis, and then Bob is going to send Alice a string that tells her which of their bases matched, like which bits their bases matched, and then that resulting information will allow them to both have the same key, but no one who intercepted any of these communications will be able to replicate their key. And like the proof for that is a bit in the weeds, so we won't be going into that. So the first step for this, obviously, if we want to create any of these random bit strings, is we need to generate them somehow in Python. And what we're going to do is use just a very, like, standard get random bits function from the random library. And we want to generate some number of bits. So the way we're going to do that is first import get rand bits from random, and then we will generate one random bit at a time. And like, there are many ways you can implement this, but this is just the way we've chosen to implement our random bit strings. So if you have questions like, oh, can I do it this way? Double check with the Python like manual, but almost like there's like 1,000 ways to generate random bit strings. It all depends on what kind of randomness you want. You can even encode, like, and seed your randomness so that you can choose like where you might have like less randomness. So there's many ways to do it. Um, so once we've generated those bit strings, or generated those bits, we will store those bits in strings. So for the first step, Alice will generate her bits randomly, one by one, and add them to her string, just in a loop. So the syntax we use to add a string to another string is just a plus, because we are generating get random bits generates like a bit. We are then casting it to a string. So this way it doesn't try to like add a number to a string. So like this is already in string form. Um, so we need to cast our random bits to a string, but then this plus just concatenates our two strings. So we don't have to do anything else. It's a pretty simple line of code, and we can just loop through and add as many bits as we want. Alternatively, if you, I kind of wrote over this, but you can also do plus equals rather than Alice bit string plus this is equal to Alice bit string. It depends on how you prefer to code it, but these are completely equivalent lines. So once we have created these bit strings, we want to store the qubits that Alice sends to Bob as a list. So Alice will generate a list of qubits one by one, similarly to the bit strings she created for her like information that she was trying to send. And so to implement this in Python, if we've already set up the like bases that Alice wants, so Alice has randomly generated a list of bases, and we may already have, and we want to like now add a qubit to this list, we can use a or we can use a function that's built in to any list. So this encoded qubits like variable is of type list. Oh, that is an A, not an I. And then we do dot append because it's just a built-in function for this variable type. And then we can add another qubit QC to this list. So the final thing that we need to be able to do is create functions. So for Python functions, you can think of any function like a black box. That's how we typically describe it, where you give it an input and it produces an output, but because it is black, it is opaque and you can't see into it. So I've actually had like exams where they'd give us like a black acrylic box and you'd have to like probe the inputs and the outputs, try to figure out what it was doing inside of it and be some random circuit. But a lot of things you can and do characterize entirely by looking at the outputs given the inputs. So functions work the same way. And we want to use functions for this in particular. We're kind of stuck with this. So we need to like if we need to keep making the same functionality over and over again, we want to only implement our function once and just call it so we don't write the same code 1,000 times. So to do this, we've seen functions a little bit before, but if you are less familiar with Python, we're doing a very brief review that we're going to use the keyword def to create a function. In this case, we're going to create a function called encode. And we have Alice's bit string that she wants to encode. So she's decided what information she wants to encode, and she's decided which bases she wants to encode this information in. And then we're going to create a list of encoded qubits that encodes the classical bits of information in the qubit bases that she wishes this classical information to be encoded in. And then she will send qubits over to Bob. And she can send these qubits over to Bob in the same way that you do like classical like quantum teleportation, not classical, like quantum teleportation like send, I guess, or you can do it like as a reverse, like a super dense code. There's a lot of ways you can transfer this information, I guess. That is the point. So in QKD, we will want to create long keys so we can send long messages. So each, and this is because like normally for cryptographic protocols, the longer your key, the better off you are because it's harder to replicate a long key. Well, if you only have a couple bits, you can randomly guess for a while and eventually you'll figure it out. But each bit of the key corresponds to one qubit that Alice has to send. And so if we're sending like a 32-bit like key, which is a bit short for a lot of things use like 256 now. But you can, we can still do all of this just by implementing the same circuit over and over again with some function. So last week, we did create some quantum circuits using functions like this create bell pair, where we first do a Hadamard gate and then do a CNOT gate. So yeah. And so this is now like, instead of just creating these circuits by themselves, we're going to do the logic to, I guess, like encode many of these bell pairs and actually distribute them. So we're not going to create any of these circuits ourselves every time, and we're just going to be using the same function that we defined once. And then at the end, we are going to run it on the quantum simulator in this case, and then there's I guess, a bonus bit where you could run this on the quantum computers themselves if you want. We're just not going to do it due to time constraints. For like, it takes a couple hours to get time on the quantum computer. So key takeaways for this portion are that key distribution is an essential step in secure communication. And we will be creating a symmetric key using a quantum channel to distribute a perfectly, like a physically secure key between Alice and Bob. And this is going to be achieved by just like distributing these qubit states that Alice and Bob can then measure in different bases. So it is unique that for these qubits, you can measure in different bases. You're not just stuck with 0 and 1 every time. You have the whole block sphere to choose a basis with n. And then we're going to use Python functions to code each of these steps to simulate this. So are there any questions for this conceptual portion? Because we're going to move to the quantum experience next. And then just as a note, we do have further reading available as usual in the slides, which will be sent out. Yeah, so for like, I do see Michael noting that, yeah, as far as we know, like because we are, like whenever you perform a measurement on these qubits, you are functionally like intercepting them. Like you're functionally like we call it collapsing your state, where we're entangling them with our measurement apparatus. And once we've already collapsed the state once, we can see that we have like a different result. So if Bob is told Alice's basis and Bob like knows his own basis and he knows what he measured the qubits in and he knows what Alice created the qubits in or measured the qubits in, no, not created, I guess, like what basis, yeah, Alice planned like to measure these qubits in, and then Bob sees a discrepancy between what Alice created and what he measured based on their bases, then they know that someone intercepted it in the middle. So that is, so because that is the case, they'll just throw out all that information. So as far as we know, there is no way to, like, you can intercept the information, but Bob would know. So that's like, it means that you can't end up with a key that you're not already aware is compromised, so long as you're checking. And the like key creation, um, like very easily already accounts for this. You can just throw out those bits. So maybe like you send 100 bits and Eve, who's normally like the eavesdropper, intercepts 5 of them or 10 of them. You can throw out those 10 bits and then keep the rest. If she manages to intercept all of them, then you can try again later when she's not looking, or like choose a different channel to send it through. Cool. So with that, I will swap to our quantum experience. Let me actually get things set up so I don't have random things open. That's not what I want. Sorry, I'm like trying to find where my tab is. Cool. There we are. So here is our Python notebook for this week. You guys should have had it sent out, so you should have it from somewhere on Canvas. Cool. Okay, so sorry, I'm like trying to get reset up. But yeah, so we're going to be actually implementing this quantum key distribution protocol. And we have like a lot of like information that you like heard in some sense in lab. I don't want to like read it off. So our the setup for what we're going to be doing this week is a 7-step process where we select our basis. This, I guess, I don't know exactly this. I'm not familiar with this syntax for it, but like this X or times or plus to encode each qubit. So if you take one to be like an energy basis and one to be a plus minus like equatorial basis, you can set, like you have, I guess, 4 options for each bit to be in. Each given like classical bit that you're trying to encode. We then select our measurement basis, where Bob will randomly select of the same bases. Alice will create these quantum states and encode them in the selected bases. So you will have these the qubits that will be sent across. The way that you'll be creating this key will be done through qubits that are encoded in particular bases. And then I'll also actually send them via a quantum channel, which like you can achieve in various ways. Normally, like it'll just be a photon down an optical fiber because that's an easy way to send quantum information. And then you can measure these states, like Bob will measure these states using the measurement bases that he doesn't know these bases are the same as Alice's bases. That doesn't matter. He's still getting information out. And since quantum states don't last forever, you do want to measure them when you get them typically. But then Alice can announce which basis she used to encode each bit. And she can just send this via the classical channel. And then for the final step, Alice and Bob will discard all the bits in their key that use different encoding and decoding bases. So, or a different, encoding and decoding basis. So Bob can compare what he got to what he would have gotten if he was using Alice's basis, because he knows what bases he used. So like he can just compare like directly his basis encoding bit string and Alice's basis encoding bit string, and then could tell Alice which of his bits matched and which didn't, and she can discard the same, and then they'll have a perfectly like an exact copy of the same key. This is called like a symmetric key like encryption protocol, or I guess, it's called symmetric key distribution often. And this is different from what is most commonly used for key distribution now, where we have a public key and a private key, and your private key is like kind of what you use, and your public key is what you can distribute. And it's very complicated how like that protocol works, or I would say it's pretty complicated. So we won't go into it, but there are proposals for creating like asymmetric or public-private key distribution protocols that are quantum. But I just want to note this is different if you're familiar with key distribution from the most standard key distribution used today. Um, so for there's also a step 8 in the real protocol. In this lab, we will not worry about the step 8 for like an eavesdropper. That's the challenge section at the end of the notebook for you to implement an eavesdropper Eve, and then to be able to discard any bits that Eve may have messed with. Um, okay. And you guys are having a chat about deterministic versus probabilistic. Um, yeah, it's a very, very good question. I have some takes, but I will wait till the end if you are still on that topic. Cool. So the first step is to import the functions we need. So we want to import get random bits, which is the only function we need from the random library. And then we also want to import the full Qiskit library just for simplicity, and we'll import this as Q. So we can use any function inside of the Qiskit library just by doing Q dot that function. That's what we're going to start out with. And again, remember to always run your import functions, otherwise things won't work. And you have to wait until the star has gone away and you have a number on your input line before it's actually run and implemented this. So for the purposes of this lab, we'll be using a key length of 500, and we will define that as you can see here. What we're going to do for a classical channel and a quantum channel. So the quantum channel would typically be photons traveling down a optical fiber and maybe going through some quantum repeaters to ensure that we have like a high fidelity state reproduced at our like at Bob's location in the end. And then we have a classical channel, which could be like, distributed by optical fiber if we wished, but you could just as easily run it through normal wires and it'll just be a bit slower. So we're going to run this, and this is just setting up, I guess, our like one, I guess, static variable we want set up. We're just going to set this to 500 and leave it like that. And we're going to be modifying our quantum channel and our classical channel by appending to these lists. So this square bracket here is just initializing an empty list, and we'll append to this list later on. So now we're going to actually go into the QKD protocol that we're going to implement. So the first step is to encode our qubits. And so I'll try to go through this function not too quickly, but there are good comments if you ever get confused. So we're going to send in the length of our key that we're going to create. So this key length here will be passed in as this length variable, which you'll see later on. And Alice needs to randomly select a bit to encode, so it can be a 0 or a 1, and then a basis to encode in, which can also be a 0 or a 1, but those zeros and ones instead correspond to either the z basis, or i.e. the 0, 1 basis, or the plus minus basis. So this here, like all this is doing is initializing an empty bit string. So the information that Alice is going to encode, and then an empty, now an empty like basis string that are the bases that Alice is going to encode her qubits in. So remember from our super dense coding lab, when we use a qubit rather than a classical bit, and we are acknowledging the possibilities of these different bases, we actually can encode more information in like a single qubit. We can encode 2 classical bits worth of information in like a pair of entangled qubits. So it's a similar kind of idea here, where if we have like the basis that we choose to measure our qubits in gives us pretty much another bit of information because we are choosing between 2 different bases that are orthogonal to each other. So all we're going to do is now append using this plus equals like casting to a string our get random bits function, and we're just going to um, create a single bit at a time. And we're going to do this exact same thing for our bases, but instead we're interpreting this as a 0 meaning to encode in the 0, 1 basis, and a 1 meaning to encode in the plus minus basis. And you'll see how this is implemented in just a second. But all this is doing is just appending to these bit strings, and then you'll eventually have like a 500 length string for each of these. And to create the qubits, for each of these, like for like our, I guess our qubit string, you will need to have both of these bit strings to encode them. So you need 2 bits of information to encode a single qubit. Okay, so now we've created these, and we're just going to look at the first 10 elements, and it'll just give us a random list of 1s and 0s. So you can see we've run select encoding of our key length. So the actual length of Alice's bit string and Alice's basis string is 500, but we're just choosing the first 10 because 500 would be kind of a mess to look at. And all we have to know is that we've actually successfully added some bits to our string. Oh, it's weird. Thomas has asked, it's weird the code has an extra pair of parentheses. I guess it's just in case you are unsure. Just add more parentheses, it will never hurt you. Adding not enough will hurt you. So I guess there's cases where I guess you can add too many parentheses like that match. If they don't match, then obviously it will cause an error, but it's generally not a bad idea to just add more parentheses than you think you need, because then you know what's happening for each step of your function, even if you think you know the order of operations that it's going to use. Okay, now we're going to do the exact same thing pretty much with Bob. It's just a bit simpler. We're not encoding any information for Bob, we're just encoding a random bases string or basis string. So for this, we're going to define a function called select measurement. And similarly, like we know we have a standard key length. So we're just going to create a key of this length by going like iterating through. I guess I didn't totally explain like this for I in range length. We'll just go through this and store a number that you're going to increment each time. So it's going to store a 0 in I. It's going to add a random bit to the Bob bases string that we've initialized as empty here. And then it will keep doing this and incrementing I. So it'll then increment I to 1, go back up here, check if I is still in the range length. So range length produces a range from 0 to length, or like length minus 1 technically. And so it will do the same thing again, increment I to 2, and then just keep going through until you're at the length that you want. So it's going to create a basic, like a string called Bob bases that is a random assortment of bits, or of 500 bits specifically. So we can run this, and then you can double check that you've created a string, which we have. Here's just 10 random bits. It doesn't matter what they are, but this just ensures that we didn't have like some typo that is giving us something else. Like we should never see a 2 in here, for example. So now we have created our like kind of initial information we're going to like send over, and we know how we're going to send it over and how we're going to measure it. So now we have to encode our quantum states. So we have this table that describes how we're going to encode the states. So if Alice's bit string at location 0, for example, is equal to 0, and Alice's bases is equal to 0 at that same location, then we're going to encode 0 in the 0, 1 basis. And we take the 0 state to be equal to 0 and the 1 state to be equal to 1, which you can see over on line 3 here. If Alice's bit string is equal to 1 and Alice's basis is still 0, so we're still encoding in the 0, 1 basis. We want to send a 1 qubit state. If instead our basis state is 1, that means we're going to encode in the plus minus basis. And in the plus minus basis, 0, like a classical 0, is equal to the plus state. And the same way, a classical 1 is equal to the minus state. And so we're just going to be functionally encoding, or we're going to have 4 different possible qubit states that we're sending based off of 1 classical bit and 1 basis choice for this encoding process. And it's this encoding that allows us to, I guess, send this information and have a way of verifying that there's not been any interception of our information. So now our encode function is a little bit more complicated, I guess. We're going to do the same for I in range length Alice's bit string. We could have also passed in another variable or defined a variable for a particular function that is of the correct length. But as it is, we're just going to check the length of our bit string. We could add in an additional like error check to make sure that the length of Alice's bit string and the length of Alice's bases is the same, because we do need that to be the case to be able to encode every single bit. But we're not doing that in this case because we just assume we coded it correctly. So this is not scalable code, but it is a little simpler when you avoid those kinds of checks. So we're going to, as our first step, we are first initializing a empty list of our encoded qubits. Just this square brackets again is just an empty list. We're then going to start up a quantum circuit. We're going to create an instance of a quantum circuit, which is using Q, which is the Qiskit library that we imported as Q earlier. And we're just going to create 1 qubit and 1 classical bit for our quantum circuit. We don't need any more bits than that. And then if our Alice bases at location I, so we're iterating through. So right now, let's say like we're at I equals to 1. If at location 0, Alice basis is equal to 0, then we are encoding in the Z basis. So then if Alice's bit string is equal to 0 as well, then we know we just want to encode a 0 state. And so because we are initializing into the 0 state just by starting up the circuit, the way that superconducting quantum circuits work and superconducting quantum computers work is all the qubits just are started in the 0 state. That's why they're kept so cold. Eventually, they will all decay into the 0 state without you doing anything. There are active reset protocols. This is what's called a passive reset. But if you just wait long enough, your quantum, and you do nothing to your quantum computer, eventually every single qubit will be in the 0 state. So that's why we always assume this. So we're assuming that, and so we're just passing in this case. If we instead want to encode a 1 state, so if Alice's bit string is equal to 1, we're still in the case that Alice's basis is equal to 0, we want to encode a 1 state. So we're going to apply an X gate, specifically a pi X. So we're going to rotate on our block sphere from pointing straight up to pointing straight down by rotating around the X axis. So that's all we're doing here. And with that, we're done with half of our encoding. The other half of our encoding is if the Alice basis is equal to 1. So that means that we are instead encoding in the plus minus basis. So if we're in the plus minus basis and we are encoding a 0 state, to go from a 0 state to a plus state, you just do a Hadamard gate. So all we have to do is add an H gate to our quantum circuit. And then if instead our bit string is equal to 1, we can apply an X gate and then a Hadamard gate. There's many ways you could do this, of course. You could also do a Hadamard gate and then a Z gate. There's a lot of options. But if you do an X gate, you're now pointing in the one direction, and then a Hadamard gate on a 1 state brings you to a minus state. So it does like a pi half rotation in both X and Z. So the final step is just to add the circuit we just created, or like append the circuit we just created to our encoded qubits list. So every single element of our encoded qubits list is actually an entire quantum circuit. So every time Alice wants to send a qubit, she has to perform this quantum circuit on her quantum computer, then transform her qubit states into like photonic states. So she has to do some kind of upconversion process, because typically superconducting qubits are in the microwave, but you can upconvert them to like light frequencies. So typically qubits operate in the gigahertz. If so, gigahertz is 10 to the 9. If instead you want to send it as light, you're going to be in the terahertz. So that's 10 to the 12. So you have to upconvert by like a factor of 3. And that's a massive like open question is the best way to do that. You can just go straight with photons. That's how most of these experiments are done now, is starting out with entangled, or when I say entangled, with single photons that you set the state of. That's really like annoying to do. Typically you do it with color centers in diamond, which are typically considered qubits. But it's just a little bit inconvenient. So being able to convert from a superconducting quantum computer to a like color center and diamond state would also be very useful. Cool. So with that, we can now encode the bits using the bit string and the bases that we created earlier. So we're going to, let me run this function first. Make sure you run all your functions that like Python knows that you've defined a function of this name, because otherwise it'll be like, what is encode? I've never heard of this before. It's not a variable. I know. Okay, so now we're going to do that. And the final step for the required content, which we're just barely going to make it through in time, but I will go through the optional content past time, and I can answer any questions for those that need to go early. Not early, those that need to go on time. I have no right to your time after 9 p.m. Unfortunately, sometimes the lab is just a bit long, which is why we put it in the optional content. And of course, this will also be uploaded to YouTube, so you can watch the remainder of it and ask any questions on Piazza or Canvas. So now Alice is going to send her qubits over to Bob via the quantum channel. It's pretty simple the way we're going to do it in code. But remember, we created this global variable quantum channel. We're just going to set this to be equal to the encoded qubits list. If you are familiar with Python, you might see, this could be a problem if we wanted, like, a list is a mutable type. So we could change both of, we could change both of these by changing my encoded qubits variable. So if you wanted to avoid this, you could import copy and then like as copy, I think. And then you can do copy.deep copy encoded qubits. And this will create, like, this will do a new, or will create like a new list, like a new place in your memory. So if you change encoded qubits, it will not change your quantum channel. So that could be a good thing to do. Alternatively, if you treat this quantum channel as actually being like part of, or as actually being like kind of persistent over maybe many cycles, you could also do quantum channel dot append encoded qubits. So it really depends on like what exactly you want to do. Because this is just a code implementation of what we're doing physically, it doesn't matter terribly how you do it, because in real life, like, you're just going to be sending it over an optical fiber. It doesn't matter how you, like, where you're storing these variables until you put them into the optical fiber. So gonna be the same kind of key takeaways, the same for the reading and resources. Are there any questions for this first half before we go to the measurement and, like, I guess, key creation step? Okay. Well, if there aren't any questions, and definitely just post whenever you have a thought, even if you think it's a stupid thought. Like, I promise it is probably very informative. Um, a lot of, like, kind of like, I mean, I don't, so I've had, like, thoughts where I was like, this is a really stupid idea, and then I'll, like, mention it, and they're like, oh, actually, that is a big problem, and you'd think that we'd be able to fix it by now, but actually, like, it's an active area of research, and we're trying really hard to, like, make it better. Um, like, so there's a lot of ideas that seem very trivial but really aren't. Okay. So now, our step 5 is Bob measuring the qubits and the random bases that he chose. This is kind of like the inverse of, what Alice did. And it's you can think of it the same way, actually, where actually, well, before we look at it, I guess you guys can all see it. But do we remember how Bob measured, um, his, like, the entangled, qubits last week when we did, super dense coding? Like, what was kind of like the key intuition for how to, look at these different states? Tomas, you are right on as usual. You want to reverse the operations that you did before. So if you have done a Hadamard gate and you've gone from, like, your equator up to 0 state, you can do the same thing. Do a Hadamard gate again. It will bring you back down, to that state. Um, so I do like you guys' interpretations of Bob. I'm glad that Bob is all of your heroes now. It's pretty cool. Alice gets not enough credit. I feel like Alice actually gets more credit most of the time. Like, Bob is kind of the underdog. Like, he's just measuring stuff. Like, he didn't have any of these planned out. Like, he just received the qubits. So I support your endorsement of Bob. um, but yeah, so, oh, I guess I also got a question from Angela. If the up conversion procedure is similar to the parametric down conversion I mentioned in previous labs. So yes, it is, like, it's, I guess, a different, like, process. So spontaneous parametric down conversion. So they're both, so while I say they're very similar is because they're both, nonlinear processes where you use a nonlinear, crystal that has some large, like, there's, like, different, like, nonlinearity parameters, typically called chi's. Like, you have a chi2, which is like a second order nonlinearity, or a chi3, which is a third order nonlinearity. Um, and these nonlinear processes allow you to split, photons. Like, you can split one photon into two photons. Um, and, like, whether that process, actually, like, maintains, like, identical photons, depends on what you're doing. But what you often do, like, for an up conversion process, you can put in two photons, um, and create, like, it's called second harmonic generation. Um, and you can create one photon, of a higher energy. And so it's something that we do pretty commonly. And so we want to be able to do this kind of process in a quantum fashion. Um, but the problem with, these processes is that they only work like 1% of the time. And spontaneous parametric down conversion works, like, way less than, up conversion. Like, maybe spontaneous parametric down conversion, they also call it SPDC, only works, 1 in 1,000 times. So these are very closely related things where you're trying to convert photons of different numbers and different frequencies, and you just have to conserve energy all the way through. But this is, like, a big, like, open question: is the best way to do this in a reliable way? Because obviously, if you're trying to send 500 bits, you don't want to have to send it 5 million times to get all this information reliably to Bob? Cool. Um, but yeah, very good question. Um, it's a very interesting like physical problem that still is like a big problem in quantum communication and quantum key distribution. Um, cool. So, and we will hopefully be going through some more, I guess, physical um, implementations and like and experimental constraints in one of like the later lectures. Um, so stay tuned for that. It'll be like probably after algorithms. But yeah, so now we're going to create our measure function. And for this, we're going to send in um, our Bob bases, our encoded qubits we've received from Alice, and a backend. So we're going to have some backend, like some quantum computer, we're going to actually measure these qubits on. So we can create a circuit, I guess, for our, or like we can, I guess we can append to our quantum circuit functionally. So using coded qubits, the way that we've written them out, in this case is they are just in circuit form still. This is not how they would be physically, but mathematically it's equivalent. So for the purposes of coding, it's a perfectly reasonable way to do it. And we're going to store this encoded qubits at I as our variable QC. So that's the quantum circuit we're going to be adding functions to. So if our Bob basis is 0 for a particular location in our length of encoded qubits, we want to measure in the Z basis. So we don't have to do anything. And we can just measure as we are. If our Bob basis is equal to 1, we want to measure in the X basis. And the X basis is the same thing as the plus minus basis. It's along the X axis. And so for that, we just do a Hadamard gate and then we measure. So that's a little bit simpler, actually. We only have 2 cases because we only have 2 possible bases to measure in. We don't have different encodings depending on what basis we want to be measured in. And so now that we've added these measurements to the circuit, we can execute the circuit in the same way we always do. And we're going to use whatever backend we sent in. We've kind of predefined the number of shots we want to take. Because we're not running on hardware, we are planning on running on the simulator. We just set the number of shots to 1 because it should like be fine with that. But if we want to, because to be clear, we are functionally always doing a deterministic measurement because when we are measuring in the X basis, we are actually rotating our plus state up to our 0 state, and then we're measuring in the Z basis. So there's no probabilities involved with these measurements. We only have to take a single shot to get a deterministic number of like what state we're in. And feel free to like run through that mathematically if it would make you like more confident in that. But it's a simple thought, but it takes some getting used to because we can't measure in the X basis just by itself. So now we're going to just execute that circuit and get our results. And then we're going to take our measured bit to be the output that has the maximum number of counts. So we are, whichever state has the most counts, that's our measured bit. And we're going to append that bit state, either the 0 state or the 1 state, to our measured bit result. And we're going to append that to Bob's bit string. So that is Bob's full job, just measuring the bits and then creating a string that tells him which qubits he got. So now we can set our backend, in this case to be the CAS simulator. If you want to swap this out to be a physical quantum computer, you can definitely do that. Just make sure to increase your number of shots because there's always going to be some error due to noise, even though it'll still be a deterministic measurement. Great. And then the so that we now have both, like Alice has her whole bit string and she knows what she should, like what she sent, and then we have Bob's bit string, which is what he measured. He doesn't actually know like what the classical data um, Alice encoded was. He only knows the quantum data he received, and the classical data he created from this quantum data by measuring it in a random assortment of bases. So now Alice can send the list of bases she used to create her encoded qubits over to Bob, and you can just use the classical channel for this. There's no quantum information here. It's just a sequence of zeros and ones that are totally classical. So she's going to put that onto the classical channel. And now we're going to do a pretty standard protocol because the quantum part is done now, actually. The unique thing is just that there's no way for like anyone to have eavesdropped without them knowing, because they will find out at this comparison step. So now Bob, like Alice or Bob can check which of his bases are the same as Alice's bases. So of course he saved the bases that he measured in. Alice has sent her bases over. And so we have both of these lists of zeros and ones. And then we just go through, we start with a empty list of indices. And for each I in the range of the length of Alice's bases, if Alice's bases at that location are equal to Bob's bases, like if Alice's basis, I guess because bases is plural, but the variable is plural, it's a bit, I don't know, it feels a bit confusing. We can append the index I, so the number that we're iterating through, to this list of indices. And then Bob will know which bits he received correctly or he interpreted correctly. So now that Bob knows which bases Alice used to encode her qubits, he can see where they happen to have, where they have agreed on these bases. So Bob will run this. And then he can send this list of agreeing bases, like these correct locations, back to Alice. And then what they're going to do is they're going to down select from our overall key to just the indices of this key where they have the same basis choice. So all they're going to do is for the index, this IDX is a very common shortened version for index. For our index and indices, we can append to our key. So we've initialized our key to an empty string. We'll append our bit string at that index. So whenever the bases match for all those indices, we'll just append our bit string to our key, and then our key will only be the indices where this occurs. There is a one-liner where you can do both of these functions in a single line for the purposes of creating the key, but you do need to send the indices back to Alice. That's why I've done this in 2 steps. So if you know that one-liner, it is very useful, but you're kind of redoing the same thing twice because you do need to get the indices by themselves. So now we can use both of these. I guess we can use this function, I guess, twice. So we're going to construct the key from indices with Alice's bit string and the information currently on the classical channels, which is this agreeing bases function that Bob put there, or agreeing bases variable that Bob put there a while ago. And this 14 line. Now I should run this. And then Bob is going to use his bit string and the agreeing bases to construct this key as well. And then we can print, string index out of range. Did I not run everything correctly? That's a bit concerning. Where did I go wrong? Search for a solution online. Oh, that's my favorite way to solve bugs. I'm just going to run it again to ensure that I have actually run everything, because maybe I just didn't run a particular function. Cool. Eh? Eh? No. Why is this not happy with me? The bit strings we're passing in should be correct. I would love to try to spend like 10 minutes debugging why I managed to screw this up. If you guys know, please let me know. If this has worked fine on your computer, I probably just forgot to run some line. Did I run everything? Does Bob know? Does Bob know the answer? Bob probably. Okay, I definitely just didn't run some line, and I'm not sure which line that is. Okay, we're gonna do it once more. Eh? No, okay, it's not happy. I think what happened is I eaved myself. Um, if you eave yourself, then, oh, no, I didn't run this. That's where I went wrong. We're going to actually run this line. I never sent my qubits. That is where my problem lies. Okay, great. So let's just go and make sure we send our qubits this time. Because if you don't send your qubits, you will have nothing to measure and then you will error out. I did not eat myself though, so that's good. Bob should have sent me a message and been like, hey, I didn't receive anything. Why are you still trying to figure out what the results are? Okay. We'll wait for that to run because that's going to take a second. Cool, that's run now. Remember the simulator will take a second to run, maybe 10 seconds, because you have to wait in line and then like actually run it, and then it should work fine. There we are. Cool. We have achieved accessing the key. If you forget to run a particular line of your code, you will get probably a similar error to what I did. So thank you, Michael. Since Bob knows everything, there was no reason for him to tell me that there was something wrong. He just knew what Alice was doing, but he didn't want to tell me, which is fine, I guess. I was the eavesdropper in this case. But yeah, all we've done is just, we do have like a pretty long key. We just assume that at least 10 of the elements were correct, because probabilistically it's a 50-50 shot each time, so probably around 250 are correct. Even for a big edge case, we're probably getting at least 10 elements correct, like that are matched between Alice and Bob. So all we're doing is printing this out, and we can also check if the entire key, all like in elements, it'll be less than 500. Let's assume it's like 250. All 250 elements are the same. So Alice's key is equal to Bob's key. So with that, we have successfully done quantum key distribution using a BB84 protocol. So there is some extra content where you can send your own messages. You can use, like, this is just the same kind of protocol, just like in one single block, and you can vary what bit string you'd like to encode. So that's pretty fun. So we've distributed our key, and now we can put in a bit string that we've created. And in this case, we're still just doing a random encoding, but we could swap out the bit string for this purpose. And so now once we've used these new keys, so let me run that keys, we can create functions that encrypt and decrypt messages. So any string that you have, every single character that you can type on your keyboard is just an 8-bit string. In reality, like it's considered like a car or a character, but it's 8 bits long, or a single byte. And so you can convert whatever string, and you can encode it, like you can use like whatever encoding you have to put it into bit form. And that's all we're doing in this. It's a bit technical, but you can definitely look up each function if you want to know more about them. This is just standard built-in functions that allow you to convert a string into a bit form. In the exact same way, you can decrypt your bit string and then convert it back into like your ASCII form or I guess like, yeah, like your kind of standard characters. Um, so that's all we're doing with this. Um, and so you can use whatever, I guess we can kind of describe how these encryption and decryption protocols work, because we are, if all of our quantum gates are reversible. So if we apply the gate, we can apply the inverse of the gate, to decrypt the message. If you do one gate to encrypt, we can do one gate to decrypt. So in this case, we're going to use an exclusive OR, where if one, like if both of your bits are one, um, then your output, or I guess like the easier way to think of it, is if um, your bit is B, and you XOR it with 1, and then you XOR it with 1 again. If B is equal to 0, B XORed with 1 is true, and then 1 XORed with 1 is 0, so you end up with 0 out if B was 1. Similarly, if B is equal to 1, um, you have 1 XORed with 0, which is true, so it's 1, and then you XOR 0 again, which is 0, and so you XOR 0 again, which is 1 because it's true. So your B is equal to 1 in this case. You'll recover your original bit regardless of what you do. So all you have to do is XOR it with the same thing twice, and you'll get what you expect out. So if we can run this just as a very like simple test, just in a single block of code, where if our message is quantum key distribution is cool, we can print this message. We can then encrypt it using Alice's key, and we'll have our encrypted message variable. We can print out our encrypted message, which will just be a random string of bits. And then we can decrypt our message using Bob's key in the encrypted message that we received. And then we can print out our decrypted message. We should get the same thing back out. So very simply, you can do that. We can change this to be quantum key distribution is super cool. And you can see the bit string is a bit longer now. We very easily just decrypted the same message again. So as your challenge problem, if you want to go further for this lab, you can implement an eavesdropper, which is typically called Eve. So Eve will perform some measurement on Alice's qubits in a randomly selected basis, and then those resulting states will be sent on to Bob. So like she measures them, and then whatever qubit state she got, she'll send on to Bob. And so since since Eve does not know the basis that Alice chose, Eve is going to mess up. There's no way that Eve perfectly replicates Alice's randomly chosen string of bases. And so Bob can compare the things that he measured with what Alice's string was and what he should expect them to be. And like you can find out where Alice or where Eve eavesdropped. There are many implementations you can use, but definitely like post your implementations on Piazza or ask why your implementation allows for Eve to eavesdrop, because if you don't check the correct way, there could be loopholes that Eve could exploit. But physically, it is possible to have it be like impossible for us to not detect Eve's presence. Okay, so with that, that is our whole lab for this week. Are there any questions on the material? Yeah, and thank you all for, I know we're 20 minutes late. This will be recorded and uploaded if you do need to review any of it. So, oh, and there's very few people left. I should have done a poll, but we have our post Zoom feedback poll. How much did this make sense for this week's lab on a scale of 1 to 5? Did it make no sense or a lot of sense? Should I have gone a bit slower? Should I tell our lead TA that we should go slower in the future? I guess I've gotten some requests for the code. I don't have it on hand, but I can find it probably. Oh, thank you, Tomas. Yes, it is 7048. I don't have the code memorized ever. Maybe I should. Um, Seems like hopefully you guys are more comfortable with the material after seeing an implementation of it. It's quite simple, but just because it's simple doesn't mean it's straightforward. Ooh, yeah, actually next week, our 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 attendance code is actually going to be encoded, and I'm going to send you the secret key rather than sending you the actual and I also need the information to decode it, but I'm not going to send you the code itself. So best of luck. Um, I mean, we might not actually. I think that'd be pretty fun. I'll propose it. I feel like that'd be too hard because then you guys have to like make sure all of your Jupyter notebooks are working. But I'll try to do it for your sake. Okay. If you guys want to do it, I will make sure it happens. Okay. So thank you everyone for attending lab this week. I hope this was helpful and I hope you have a wonderful week. And I will see you next Tuesday. Okay. Thanks everyone for your great questions and your like active participation. Yeah. Okay. Bye.